So in the last video, we solved the harmonic oscillator using the factorization method. And this one we want to try and do it analytically. And this is going to look a lot different, but it's going to give us the same answer, which is pretty cool. So let's go ahead and start. We'll just write down our equation. So a good way to start trying to solve something like this is to do some substitutions and try to make your life a little easier. So we have this, we can define this dimensionless variable. We'll call it eta. And it's going to be the square root of the mass times omega over h bar times x. So the differential of this is going to be that, and we can just substitute d eta squared for dx squared here, which is going to give us this. And then this first term here is going to cancel out like this. So we have negative h bar omega over 2 times this second derivative. And then the rest is the same for now. But now when we divide by negative h bar omega over 2, it's going to look a lot nicer, because we're going to get here, there's going to be a negative sign. And this is just eta squared, so that's pretty nice. And I'm going to rename this variable k. And so k is just our energy in units h bar omega over 2. And already you should be seeing some similarities to these different quantities that showed up in the last video. Things are starting to form a pattern, like h bar omega over 2 and the mass times omega over h bar. These are all things that you see frequently when you're working with the harmonic oscillator. So now we have a differential equation that looks simpler, which actually it's not actually. It's the same equation. It's just a little easier to work with, and we can more efficiently examine its behavior. So let's start by looking at what happens at the extremes. So, for example, when x gets large, so when the absolute value of x approaches infinity, we'll have eta approaching infinity as well. And then this eta squared term is going to completely dominate over our k here, which is just a constant. So we have an approximate equation that we can look at and try to gain some clues as to what our exponential behavior will be, if any. So this happens to be an equation that we can solve rather quickly. It's a linear differential equation of second order, so it's going to be the general solution is going to be a linear combination of two independent solutions, two linearly independent solutions. So this is what we have. This is the general solution. And you can check for yourself that this actually works. So what we can do now is look at this term and say that, okay, well, if eta is going to get really huge, this is obviously going to blow up, and this cannot be a physically acceptable solution, so we can just get rid of it. And now we've obtained a nice approximation when eta gets large. So, but we're not so sure that this is going to be a constant because we don't really know what happens when eta is small, and it's more likely that this is going to be some function. We'll just call it h of eta because it's going to depend on eta. So now what we want to do is try and rewrite or try and look at our equation a different way and try and get rid of this exponential term here so we can see what's going on over here. But this is what our solution will look like. We just need to figure out exactly how h of eta is going to behave. And the way we can do that is we can start taking derivatives with the plan that we're going to make some substitutions and try and peel off this term. So the first derivative of this wave function with respect to eta is going to be this. And then we can compute the second derivative. Just have to be a little careful with the product rule. Make sure we don't miss anything. And I wrote this down beforehand so I don't mess up here, if you're wondering how I'm doing it so fast. Okay, so that's good. So let me rewrite what we were initially trying to solve because we're going to use something here. This was the equation that we're trying to solve. And we have that this wave function is equal to this up here, this h function times the exponential. So now we can substitute this for this, and what's going to happen is these terms are going to go away, the exponential, and so is this eta squared term. Let's just write it out fully and then do the cancellations one by one. So we can clearly get rid of this. And then this is what we're left with. So these terms go away. And we have a new equation we're looking to solve now. Oops. Okay.